So we continue with the NP completeness theory. So we have already shown, not shown, at least I have told you that there exists one problem which is called SAT, to which every problem in the NP clubs can be polynomial time reducible. So I tell you one more representation of Boolean formula is called the 3CNF SAT. This is also very well known, that's why I am trying to tell you about this. What is this 3CNF SAT? Every Boolean formula which is included in the SAT problem can be also expressed by some transformations as in a very particular form, canonical form. What is that canonical form? Is this: it can be expressed as a collection of clauses which are separated by AND. So these are the clauses which are separated by AND operator, and there are only three literals here. So maybe x1, x2, x3, here maybe x1 bar, x2 bar, x3, here maybe x1 bar, x2, x3, maybe. I mean, this is just an example. So the property of 3CNF SAT, the form of 3CNF SAT formulas are like this. It's a collection of clauses separated by AND operator, and each clause consists of three literals which are separated by OR operators. So every Boolean formula can be converted to this form, and this conversion can be done again in polynomial time. So what does it mean? The problem SAT can be reducible in polynomial time to the problem 3CNF SAT. Why is it so important? Why 3CNF SAT came into picture at all? This is because this, instead of SAT, which can take any form, implication and all those, you can eliminate all the implication, by implication, not, sorry, you cannot eliminate not, implication and by implication, and actually express the formula like this. So this is a little bit more systematic form. You know that there are clauses which are separated by AND, and each clause has three literals which are separated by OR. So this particular form is very useful in reductions. Very seldom people use SAT, actually the SAT problem for reduction. They use the 3CNF SAT and reduces the 3CNF SAT to some problems to show that that is NP complete. That's why it is very important. I will not show how one can convert a formula from SAT to 3CNF SAT form. If you are interested to see it, it's a very routine task and it can be done, and you can see it in the book, the Corman Rivest book. It has been given there. So just to tell you that the formula can be expressed in this form, and most of the time people use this form for reduction because this is more, it has more structure in it than a very general Boolean formula. One can use this particular structure, that there are three literals, they are odd, and the clauses are separated by AND. This structure they can use in the reduction easily for a problem. So that much I will say about SAT and 3CNF SAT. Now let me move to the ultimate goal of this particular portion of our class, is to tell you about NP completeness. This is the term you will be hearing very often. Some problem people will say that this problem is NP complete, I cannot do anything. First of all, this statement is wrong. I cannot do anything, one cannot say, but in a sense it is also true. If somebody says that a problem is NP complete, what does it mean? It means that nobody till today has found any polynomial time algorithm for that problem. Not only that, if that problem can be solved in polynomial time, all problems in the NP class can be solved in polynomial time. It only means that. So if somebody tells you this problem is NP complete and I cannot solve it, first of all he is wrong, because he cannot say that it cannot be solved at all because nobody knows. But in a sense, he is correct also. It is very unlikely that you will be finding the proper solution, the polynomial time algorithm for this problem, because if that can be solved, the entire class NP will be solved in polynomial time, and that will be a remarkable result in computer science. This is one of the open questions still remaining in computer science, to know whether NP is equal to P or not. So this is the famous question, NP is equal to P, whether this is true or not. Don't cancel out P here and N is equal to 1. I have seen, don't laugh, I have seen people doing it. Okay, so this is non-deterministically polynomial is equal to P or not, that is the question. So this is a question which is very well known and still unsolved problem in computer science. Okay, now let me tell you what do we mean by the NP complete problems. So I am defining now what is an NP complete. I just told you what is an NP complete problem. I am just defining now in a very formal sense. A language L is NP complete if there are two conditions. First of all, you have to show the problem is in NP. That's the first task. And most of the time it is very easy to show. L belongs to NP. Second, what you have to show that L prime is polynomial time reducible to L for every L prime in NP. So this is the definition of a NP complete problem. First of all, you show that the problem is in NP. Secondly, you have to show that all problems in NP can be polynomial time reducible to L. But that task has been made easier for us, because some problems we already know NP complete, like SAT already satisfy these two conditions. I have already told the SAT is in NP, and all problems I told you can be shown that it can be polynomial time reducible to SAT. So at least we know that SAT is NP complete problem. So if I replace this L prime with SAT, automatically it is done that all problems in NP is polynomial time reducible to L. Okay, so this is the definition of NP complete problem. So let me define the class NP complete class. NPC is a set of all languages where L is NP complete. So this is the NP complete class. Then I have already, so this is the claim. I already have told you about this, that SAT is NP complete. 3CNF SAT is NP complete. Why? This is because SAT can be reduced in polynomial time to 3CNF SAT, and 3CNF SAT is, and 3CNF SAT is in NP. Because of these two reasons, 3CNF SAT is also NP complete. Okay. Now let me tell you how to prove something NP complete, a little bit elaborate. So first of all, this is the claim. Suppose L1 and L2 are two languages, so that L1 is polynomial time reducible to L2. Now if L1 is NP hard, I did not define this term yet, I'll define NP hard, and L2 belongs to NP, then you can say that L2 belongs to NPC. Let me go back to the previous slide. I will come back to this slide. Here, the NP completeness. Here, in the definition, there are two conditions for a problem to be NP complete, 1 and 2. Now suppose somebody has shown only 2 for a problem, not 1. Suppose somebody cannot show that the problem is in NP, but he can show this. That in that case, that problem is called NP hard. So a problem is NP hard if only 2 is satisfied. So definitely all NP complete problems are also NP hard. By definition, if 2 is satisfied, we say it is NP hard. So NP complete problems are also NP hard. But there are problems for which it cannot be shown probably that it belongs to NP. So NP hard problem is harder than NP. That's why it is called NP hard. It is why it is called NP hard. It means this problem is at least as hard as NP. Because you have shown that all problems in NP can be reduced to this problem by 2. So this problem must be at least as hard as the problem in NP. So that's why it's called NP hard. And if that problem belongs to NP, then it becomes the NP complete. It completes that class. Okay, so this is the notion of NP hard. Now, this is the claim. If you take two languages L1 and L2, so that L1 can be polynomial time reducible to L2, and suppose you have proved that L1 is LP hard, you don't have to show that L1 is in NP. Suppose only thing you have shown that L1 is NP hard, that is all problems in NP can be reduced to L1, suppose. And L2 belongs to NP, then L2 must be in NPC, because then 1 and 2 both are satisfied. The condition for NPC, the first condition is satisfied here, L2 is NP. The second condition is satisfied by this, if L1 is NP hard. Because if L1 is NP hard, again I repeat, all problems in NP can be reduced to L1. By this reduction, in conjunction with that reduction and this reduction, all problems can be reduced to L2 also. So that's why if these two conditions are satisfied, then L2 is also NP complete. Now, what is the generic steps to show something is NP complete? So, a generic steps, a generic NP completeness proof thus follows the steps below. What are the steps? First, you prove that the problem given L2 is in NP. That's the first step. The problem you are trying to show to be NP complete, first you prove that it belongs to NP. Second, select, and this is here comes the question of your judgment, which one to select. Okay, there is no hard and fast rule that this problem has to be selected. So select a known NP complete problem L1. You select known NP complete problem L1 and find a polynomial time reduction or this reduction or transformation, polynomial time reduction or transformation, so that this transformation should be such that if x belongs to L1, you can prove that if and only if fx also belongs to, that transformation is f belongs to L2. So actually just one is most of the time very easy to show. It is the two which is, there are many judicious choice you have to make. First of all, given the problem L2, you have to take the right problem which can be reduced to this problem. In a sense, every problem should be reducible to every problem, but to show some problem will be very easy for your reduction, and some problem will be really tough for your reduction. We'll take some examples. You will have this idea more clear when you take the examples. So given to show some problems to be NP complete, you have to choose a right NP complete problem which can be reduced to this problem. There you have to make a choice. And that is left again in this course, as we have seen already. Something is, you cannot just formalize it in a hard and fast rule. That is your judgment. You have to make a judicious choice. That is the first part. Second is, and these parts are very not independent. One is dependent on the other. Then you have to make this transformation, polynomial time transformation. You take the instances of the NP complete problem, you transform it to the instance of the given problem, and that should be done in polynomial time. And the reduction should be such, again this is not independent of the next step. You have to make the reduction in such a manner that you can show that if x belongs to L1, then fx belongs to L2, and vice versa. All these three steps are very linked together. You cannot just take one first, then second, then the third. The second and third will tell you which one to choose, which problem to choose. And third will tell you how to transform. All these are very, very much linked. And this step is non-trivial, I am telling you. This step is really non-trivial sometimes. We'll see some of the examples, but you need to have some practice about these reductions. Now, so what is the scenario now? We have all these things, what we know now. We have this class business here. We know this is the NP class. Somewhere NPC, NP complete problems are residing here. P we know is residing somewhere here. But nobody knows whether P has an intersection with NPC. If P, see, if this is the case, then we know this everything is same by our theory. If we know that if there is an intersection between P and NPC, then everything NPC, P, NP all are same. Because if any problem from P is in NPC, what does it mean? That NP complete problem is polynomial time solvable, and we know that entire class then NP should be polynomial time solvable. So we don't know whether there is intersection between P and NPC. This is not known yet. This is the biggest question. Still lying open. So I finish with this note. We don't know whether the class is this or the class is this. Nobody knows. So I hope someday this question will be resolved. But for the last, how many years? It may be more than 30 or 50 years. This is lying open. I don't know exactly how many years, but this is one of the oldest questions in computer science. Okay, with this note I finish today.